I'm very honored, really, to be in this distinguished company. And I'd like to thank the organizing committee for inviting me. Now, this talk, I'm especially honored because this talk is going to be a little different from most of the talks here. The point is that I don't think we should maybe bring it up too much because we're going to need another. Okay. No, don't leave it because there's going to be another one now. Yeah. So mathematically, game theory is not a unified discipline. I mean, it's unlike any of the talks that I heard over here. I have to confess I didn't go to each and every one, but I went to quite a few. And all those talks were about a mathematically unified discipline, okay? Now, game theory is not a mathematically unified discipline. It is not characterized by its tools. It's characterized by its applications. So we have tools from various mathematical disciplines, including measure theory, soft analysis, Banach spaces and that stuff. We have Polish set theory, analytic sets, and Borel sets, and that kind of stuff. We also have axiomatic set theory. We'll see maybe in the course of the talk some of that. We have, lately especially, we have strong use of mathematical logic. We have algebraic topology. We have probability, and we have various others. It's not something where, like sometimes you find in mathematical physics, where the subject matter is sort of requires the use of new mathematical tools. In game theory, what are used are as mathematical tools that are there already. And I think that says something for mathematics, that it has produced the tools that are necessary for many applications, even before those applications became apparent, yes? The tools are there, we use them, and that is the sense in which it's a part of mathematics, but it's different from, in the sense that I said, from other mathematical disciplines. And what holds it together is the area of application. Okay, so we have many different, it's a very rich theory, many different kinds of applications. They are all, in one sense or another, in the area of rational interaction. What I mean by rational is people who are goal-oriented, or not necessarily even people, as we'll see. They could be animals, flowers, computers, companies, nations. They are goal-oriented, and they want to maximize something, and they go ahead and they do the best they can to maximize that something that they're maximizing. When we talk about interaction, what I mean by that is that basically the players, the elements that are involved in this business do not have similar goals, usually. Sometimes they have similar goals. Usually in the applications, the players do not have similar goals. Okay? Let's keep this down here, otherwise we'll get into a game between these various these young projectors. So let's keep this down here. Now, the most important area of application is economics. Nowadays, game theory is a very, very big item in economics, especially in economic theory. Okay, it may be also in the Bank of Israel, but and not to talk of the Fed, the Federal Reserve Bank, but it's big over there also. But over there, they also occasionally use some other disciplines, macro, this or that. In economic theory, in theory, it's really on the horse. I would say that well over half of the papers published in journals of economic theory, including a journal which is called the Journal of Economic Theory, are in game theory, in straight game theory. So it has become very big. There was a Nobel Prize in game theory given about 5 years ago, in '94. One of the recipients was John Nash, a famous mathematician. And so it's a big item in economics. It's very important. It's very basic in economics. But it's not the only area of application. We have other areas include computer science. See, in computers, there are two ways that game theory comes into the picture. One is in distributed computing, where you have lots of different computers that are trying to do something, and there problems of coordination come in, and we think of the computers as players. Another way is in crashes, where one tries to imagine worst possible scenarios. One takes as a player is some devil who tries to make the system crash so as to get the worst possible scenario. But actually, as we know, to our chagrin, there really are such devils out there, and they're well motivated to wreck the system. I don't know what motivates them, but if it was, this some kind of enemy or something like that, but these people are just in it for the fun of it, and okay, no more about that. So we have computer science, we have politics. Domestic politics is an important area of application. We have a number of areas. One is elections, okay? The theory of how to run an election is a very complex matter, as we saw in the elections in Israel recently. I also have to tell you a little story. I was once at a meeting of the mathematics department of the Hebrew University of Jerusalem, and we had to pick a number of candidates to present to the dean for a smaller number of slots. So we had to pick, let's say, 2 out of 4. There were 4 candidates, and we had 2 slots. And then at some point, the chairman, this is many years ago, I won't identify the people involved, the chairman said, well, how should we run this election? I said, well, I don't know, but we have an expert on the sub-area of game theory called election theory. His name is Bezalel Peleg. Ask him, he was there. So Peleg suggested a method, and this method was adopted for the purpose of that meeting. And some outcome, some 2 out of the 4 were selected, okay? And the next morning, the chairman met me, and he was very angry with me. I said, why are you angry? He said, most of the Institute of Mathematics at the Hebrew University is opposed to these 2 that were selected by Peleg's method, essentially your method, because you suggested Peleg, and not only that, there's a specific pair of 2 candidates who most of the Institute of Mathematics prefers to those 2 who were selected. I said, Mr. Chairman, that's correct. I didn't say Mr. Chairman, but as I said, I don't want to identify the person. Yes, Mr. Chairman, that's correct. But there's a theorem, yes, that says that there's no method that will avoid this anomaly. He says, you and your theorems, yes. This is an internationally famous mathematician. I won't say in what area, okay? An internationally famous mathematician. You and your theorems, he says. So I said, okay, Mr. Chairman, I'll show you. You're right. There's specific 2 that most of the Institute would have preferred, but there's another specific 2 that most of the Institute would have preferred to that pair, and another pair that most of the Institute would have preferred to that pair, and then the pair that was actually selected, most of the Institute would have preferred to that pair. Okay, so there's a cycle over there. Yes. There's a cycle. This is well known, okay? This is called the Condorcet paradox, okay? But the chairman didn't want to hear about theorems or paradoxes or things like that. Yeah, it's an important area, domestic policy. Another important area is the question of there are matters of distribution of power. They have to do with how governments are selected. So there's a lot of theory in there. And maybe there's even a little empirics in there. Okay, we have international relations. We have, which is a very important area of application, we have law. We have social psychology, which is not really very much on the side of mathematical game theory, the social psychology, but it's more experimental stuff. But still, there's a big intersection. There's a big, how shall I say, intercourse over there. Evolutionary biology, I hope we'll have more to say about that in the ongoing. Evolutionary biology is heavily influenced by game theory in the last 20 or 25 years. Over here, the actors do not seem to be rational, but they behave like rational actors. Bees, flowers, animals of all kinds, plants of all kinds. It's a very important interaction over there. We have philosophy, we have management, statistics, military tactics, search, inspection, cost, allocation. And the important thing about game theory is that many of the theories of these things, like in economics or in politics, there's an ad hoc theory which treats each of these things differently, okay? There's a theory for oligopoly, there's a theory for perfect competition, there's a theory for elections and so on. Different theories for these different things. But game theory treats all these in a unified way, okay? Applying the same principles throughout. So it's like we have a theory of magnetic fields, of electrical fields, of gravitational fields. It's a unified field theory, one might say. Okay? So now, let's get on with it. So I'd like to be a little formal, but without using symbols. So you'll have to imagine the symbols. Some of these, of course, we're here in a mathematics conference, but still, I don't believe that mathematics is about symbols, so I'm going to try to stay away from symbols. It's not about, it's about logical thinking, intricate logical thinking. That is what mathematics is about. It's not about symbols, so we'll try to stay away from symbols here. So formally, and I put it in quotation marks because it's not really formal, as you can see. So a game consists of a set of players. By the way, let me apologize to those of you for whom this is very familiar. I think I won't be saying something new when I tell you that game theory is not precisely in the center of mathematics, okay? So not all mathematicians can be presumed to know even the fundamental definition. So I apologize to those of you who do. Let me go ahead. A game consists of a set of players, so it's a set of items called players. And then we have possible actions for each player. And we have a payoff function assigning a numerical payoff to each player for each choice of actions by all players. So the payoff to each player depends on what all players get. And there's a specific kind of game which is rather important in the theory. It's called a two-person zero-sum game, and a two-person zero-sum game is, or a two-person game is called zero-sum if for each choice of actions by the players, the sum of the payoffs of the two players is 0. Now, it wouldn't matter if the sum were 1 or 10 or whatever. It has to be constant, which means that whatever one loses, the other gains. Whatever one gains, the other loses. It's a strictly competitive situation. There is nothing going for cooperation. There's no point in the players cooperating because of this structure. Now, I have to say right away that game theory started with, for many years, it was limited to two-person zero-sum games. And I have to say immediately that none of the applications of game theory are zero-sum. Yeah, so zero sum is an outlandish assumption that has nothing, no importance in the applications. But it's a very important cornerstone of the theory. So when I say cornerstone, it's out there in one corner. It helps hold up the building. It's very important in that it's not the centerpiece of game theory. So that's not what game theory is about. But it's a very important extreme case. Not a special case, an extreme case which you use to hold up the theory. Okay, now another very fundamental concept is the concept of equilibrium. So, first let me explain what a strategy is. A strategy for a given player is a complete plan of action for that game. Like in chess, you have to say, okay, a strategy for white would consist of pawn to king 4, and then if black does a pawn to king 4 also, then I'll go knight to queen bishop 3 or whatever, yes? So if. So it's a strategy, it's a complete plan of action that specifies what each player is, what that player, a strategy for that player is to do in each contingency. A tuple of strategies, I said I will avoid the use of the word of symbols. So I'm not going to say an n tuple, okay? N is the number of players. A tuple, one for each player, is a tuple, like an n tuple, okay? Is an equilibrium, and this is a notion which is, well, it's not really due to Nash, it's due to Auguste Cournot, who worked and lived 100 years before Nash, French economist, mathematical economist, one might say. But Nash really nailed it down. He generalized it, he put it in the right framework, and he proved the existence theorem. So a tuple of strategies is a Nash equilibrium if each player's strategy is best possible for him, given the strategies of the others. Okay, so we're in a situation where the strategies are in some sense considered to be there in the whatever, considered to be there, and each player is playing rationally given the strategies of the other players. A very important concept is that of a mixed strategy. So that's a probability combination of strategies, or pure strategies. This is a pure strategy. So a mixed strategy is a probability combination of pure strategies, which means I do this with a certain probability, that with a certain probability. Here's an example. Okay. So here we have two pure strategies for each player. This is a box, yeah. We have the red player chooses a row, the blue player chooses a column. All right? And then we have the payoffs are listed in the resulting box with the appropriate colors. And now we have here three equilibria. Okay? The one is upper left. You see, 2 is larger than 0. So given that the blue player is playing the left column, the red player can do no better than play the top row. So upper left is an equilibrium, and lower right is an equilibrium for the same reason. And there's also another equilibrium, which isn't so apparent, which is for the maybe I should have just put this in for the column player, for the row player to play his top row with probability 2/3. And his bottom row with probability 1/3, and similarly for the row player, he would play, I guess, 1/3, 2/3. And this is it's a mixed strategy equilibrium, so we have three equilibria over there. Now we have the first theorem in game theory is the min-max theorem of von Neumann. Every finite two-person zero-sum game has an equilibrium in mixed strategies. Moreover, there is a number v, called the value of the game, such that the first player strategy in that equilibrium guarantees that player at least v. And the second player's strategy guarantees him at least minus v, that he won't have to pay more than v. And that's the value of the game. So in two-person zero-sum games, and that's what makes them special, there's something special about equilibrium that they guarantee the result, okay? It follows from this that all equilibria have the same payoffs. Okay, and the proof is by separation of convex sets. And then comes the important work of Nash, for which he got a Nobel Prize. I don't think he would have gotten the Nobel Prize in mathematics if there would have been such a thing. Because mathematically, while this is not trivial by any means, yes, it's not very deep either, okay? But it's very, very important in the applications. I mean, it's very fundamental in economics now and in other applications of game theory. It's very, very fundamental. And sometimes proving the important things in mathematics are not necessarily the most difficult things, okay? Sometimes things can be very, very difficult, and they can be forgotten after 20 or 30 years. And this is something which is not very difficult, but it's very important. Another thing like that in mathematics, by the way, not in game theory, is I think the diagonal method of Cantor is not very difficult at all. Yes, a school child can understand it and does understand it, but it has had a tremendous impact on mathematics in the last 150 years. For example, Gödel's work and so on is based on this, but many other applications. So it's not something very deep, but it's something very important. And many things in mathematics are like that. So the general equilibrium existence theorem says that every finite game, no matter what the number of players, what the number of strategies, has an equilibrium in mixed strategies. Okay, it doesn't have to be in pure strategies. Okay, now let's just mention quickly some of these problems, because I'm going to mention some problems afterwards. Maybe they'll be known in 50 years as Aumann's problems, okay? But here's some problems of Harold Kuhn. They were published in 1950, just about 50 years ago. When game theory was young, it was about 6 years after the publication of the famous book by von Neumann and the economist Oscar Morgenstern, Theory of Games and Economic Behavior. And game theory was riding a high tide in mathematics, which it isn't at the moment. And now it's riding a high tide in economics. So this is an introduction to, in Kuhn's introduction to the contributions of the theory of games 1. As you see, this was a mathematical publication. It was published by Princeton University Press in the Annals of Math series. So I'll mention some of the problems, and they've practically all been solved. And some of them turned out to be very, very important and central, as we'll see. So his first problem was find computational methods for solving two-person zero-sum games. In other words, finding the optimal, finding the equilibria, and finding the value. And this was proved, this I think was already known at the time that Kuhn wrote. This is equivalent to the problem of linear programming. There's an equivalence between two-person zero-sum games and linear programming. And at the time, I mean, I think we've come a long way in linear programming, but we've come an even longer way in computational ability and computational power in the last 50 years. So the problem of finding really efficient algorithms has become less important. Anyway, it's equivalent to linear programming. What you can do with linear programming, you can do with this, and you can do a lot with linear programming. This is for the two-person zero-sum case. For the two-person non-zero-sum case, there was a very important paper by Lemke and Hausen in the 60s. What's it called? Complementary something or other. Who knows? Anyway, they solved the person of two-person non-zero-sum games, okay? Which is an order of magnitude higher than the n-person games. This was Wilson and associates who successfully attacked the problem of n-person computation, computation of equilibria in the 90s. It's just a few years ago. Then problems 3 to 7 in Kuhn's list had to do with two-person zero-sum games with infinite strategy sets. That area was fairly well explored during the 50s already. There's something in the theory of n-person games called von Neumann-Morgenstern stable sets. This is the fundamental concept. By the way, von Neumann and Morgenstern did not define equilibrium. This is a contribution of Nash. Okay? They did not define the fundamental notion of equilibrium that I had here. They had a different idea of n-person sets. A very, very sophisticated, very beautiful idea. I won't go into it at all over here. But the problem of the existence of these stable sets was open for many years. Well, Neumann thought that they were, but it turned out that this was incorrect. Bill Lucas found a counterexample in 1969, which made page 1 of the New York Times. So at the time, it was considered a very important problem. I think it is an important problem. The theory of stable sets is not in the forefront of game theory now, but it's a very nice concept. He raised the problem of communication costs. And I think that has also been dealt with, although I think this somehow has receded into the background of I guess I should maybe take this away at this point, has receded into the background of the theory. A very important concept is one of values of n-person games. The idea here is sort of similar to the value, which is somehow the right answer. The way to evaluate a two-person zero-sum game is with its value. Is there some way to assign a value also to general games? This was unknown at the time that Kuhn wrote. A few years later, in 1953, Lloyd Shapley did devise a concept of value which has turned out to be very powerful, very, very widely used. His 11th problem, Kuhn's 11th problem, is very important. The question of devising special or finding special properties of games with many players, a very large number of players. So here we have two kinds of models. We have asymptotic models as the number of players approaches infinity. We have the continuum model, where you look at the set of all players as a continuum, okay? Maybe it's crazy to look at people as constituting continuum. Each person is an individual. I think it's Dr. Seuss who once wrote, a person's a person no matter how small. It's in Horton, he is a who. I don't know how many of you know that, but it's an important line. A person's a person no matter how small, but no, you see, not in the continuum model, okay? In the continuum model, you look at a set of people or a nation or an economy as a liquid or something like this, yes? And this was devised in the 60s and thereafter, and there are important connections between the continuum model and the asymptotic model. I was very pleased to hear Lovash's talk, which made this this connection in a conceptual way between the continuum and the asymptotic models. We have the problem of information. which was successfully attacked by Kuhn himself and in a more fundamental way by John Harsanyi in 1967. Harsanyi got the Nobel Prize for that contribution. We have a very important question, which is a dynamic theory of games, okay? By a dynamic theory, we mean, can we somehow look at a game situation like a physical problem where in some sense, the given situation leads to the next situation. We get some kind of differential equation or something like that. Partially, the question is answered by the theory of stochastic games, which was initiated by Lloyd Shapley in 1953, and the theory of repeated games, which was initiated in the late 50s and the 60s and worked on heavily thereafter. But it's only a partial answer because those theories are not truly dynamic in the sense that it's not that the current thing leads to the next one. These are theories about games that are played over time, so in that sense they're dynamic. But they're not dynamic in the sense that, how shall I say, of the current situation leading to the next one. In some sense, it's some kind of differential equation, a difference equation, or something like that. That kind of concept is represented by the theory of evolution, to which I referred before. Darwin's theory of evolution, evolutionary stability, and evolutionary dynamics. This was initiated by a biologist by the name of John Maynard Smith, together with Hamilton, another biologist, in 1972, and has really taken off in the quarter of a century since then. It's a very important, very, very important fundamental concept in game theory, and it's going to be more important in the next century. Then we have finally non-transferable utility in coalitional games. I won't say any more about that because I want to get a little bit into substance. Okay, this is also an important concept which has been solved. So essentially, all these problems were solved. So that's the end of the introduction. Let me just quickly, this is a sort of a kaleidoscopic approach, okay? It's not really, I'm sort of trying to bombard you with verbal images rather than, this gives you some impression, impressionistic talk, not very detailed. So the plan of the lecture is we're going to talk about this problem of dynamics. Stochastic games and repeated games is one corner of it, and I said that's not truly dynamic, and then we have biology, which is the truly dynamic thing. In the matter of many players, we're going to talk about the core of a market, which is a purely game theoretic concept, and its relation to purely economic concepts like the law of supply and demand. We have values associated, Shapley values of games with many players, a very important area, applications to cost allocation, especially telephones and other applications of cost allocation. We have strategic models with a continuum of players or with many players. See, when you're driving along a road in the morning trying to get to work, then we can apply these models where there's a sort of, we look at these automobiles as a continuous flow, okay, a continuum of players. This is a very useful way to look at these things. By the way, there is an example, and I think it's not very pathological, in which building an additional road actually changes the equilibrium of the game in such a way so that it takes everybody longer to get to work than before the road was built. So we have an equilibrium, we have a road system, okay? Very simple, I think 4 or 5 roads getting one place to another. And then some official decides to put in several billion pounds or a shekel to build an additional road, and they build the additional road, and the equilibrium changes, and now it takes everybody longer to get to work and back. That's with the new equilibrium. Okay, so these are strategic models with many players. We have a very important area called perfect information games. This impinges on some of the deeper mathematics in this in-game theory, algebraic topology, logic, set theory. There's Martin's famous theorem in 1975 has to do with this. And we're going to try to talk about some applications, really engineering applications, which are used nowadays of quite complex and deep game theoretic results, and they really work out there, okay? It has to do with it's called the National Resident Matching Program in the United States. We're talking about thousands of hospitals, tens of thousands of interns, how to match or medical students, how to match them to the hospitals. We use deep mathematics in there to get that job done. Let's see. For the future, I'd like to say briefly afterwards, or maybe now, what it is that we're looking at in the future. We're looking at the idea of coalitional games with incomplete information. Okay? Okay, so for the future, I think one of the very important problems is coalitional games with incomplete information. The theory of strategic games, of Nash equilibrium, or of strategic equilibrium in general, with incomplete information is by now well understood. I mean, this was started with the work of John Harsanyi, for which, as I said, he got the Nobel Prize, and is now well understood. The problem of coalitional games with incomplete information is not at all understood. This is something that we're scratching the surface of, and I think we will make, at some point, somebody will make a concerted effort, and this will come into the forefront of game theoretic research in the next decades. The problem over there is that in a coalitional game, a coalition of players has to get together and try to cooperate in order to achieve some goal. And when we have incomplete information, so we don't know, the players don't know what the other players know, then there arises a problem of communication. There arises a problem of credibility. These things are very complicated in the coalition case, and there is no good definition of that yet, not to speak of theorems, yes? I mean, there are works about it, but the works are, shallow. They do not address the correct problems. And I think the people who do this realize that. Yes, there's a very important work by Bob Wilson, who is an excellent game theorist, from the late 70s. Beth Allen at Minnesota and others have worked on this, but none have really gotten to the core of the problem. So this is very important. Another important problem is that of computational costs. This is, again, a very fundamental problem. Computational costs means that, and this has to do not only with game theory, but it impinges especially heavily on game theory. Computational costs is the problem where in order to do something right, you have to figure it out. Okay, so you have to sit down next to a computer with pencil and paper, whatever it is that you're doing, and try to figure out what to do. But how much are you going to invest in this computation? Well, in order to find out how much to invest, you have to do an even bigger computation. So you're in trouble over there. There's a conceptual problem over there, and this has proved very, very difficult to crack. I once gave this to a doctoral student. Somebody wanted to do a doctorate with me, And that really was unfair, because to a doctoral student you have to give a well-defined problem, not a conceptual problem like that, yes? And he really didn't do anything with it, and afterwards I gave him a well-defined problem. He did an excellent doctorate, okay? But it took wasted 2 years of his time. So that's a very important. Now, evolutionary dynamics is a very important thing. We'll hear something a little later about evolutionary statics, which turn out to be very, very similar to strategic equilibrium. But evolutionary dynamics is, in other words, you get some kind of cycles or waves or whatever it is that you get. This is not yet well understood at all. This is the next thing. And then there are some very important problems in the area of repeated games and stochastic games. We really are only at the beginning of this, although some of the deepest work, mathematically the deepest work in game theory has been in the area of stochastic and repeated games. Nevertheless, very, very much remains to be done. Basically, we have only done part of the two-person theory. A little bit into 3 or 4 players, but not very far. And there's a lot of work to be done in repeated and stochastic games. Like I said, this is an area where a game is being played over time, and we're looking at the equilibrium of this game over all of time. So we're planning also what to do in the future. It's not truly dynamic in this game. Let me give you the idea, the definition. So a stochastic game is a long or an infinite sequence of games that are played sequentially, one or after the other. The games are chosen from some fixed finite set. At each stage, the payoff for that stage is determined. And also, in addition to the payoff, is determined what the game is to be played at the next stage. And then you average all the payoffs. Okay, a very famous example due to Blackwell and Ferguson in 1969, that's David Blackwell, a famous mathematician, mathematical statistician, is called the big match. Here we have a situation where the row player has to pick either the top or the bottom row. If he picks the top row, he gets the payoff that's written there, 1 or 0. It's a zero-sum game, so the other one gets paid minus that amount, so minus 1 or 0. And the game is played again, same game. Okay, but if he plays the bottom row, the game is over. That's the big match. See, the game is over, and then that payoff, which is written in the box that was chosen, gets paid forever. It's a very subtle, very difficult game. I mean, nothing could look simpler than that. Nothing could look simpler. But it's very, very subtle, very difficult. It turns out that there is a value. All stochastic games have a value. All stochastic games have a value. It's a theorem of Mertens and Neumann in 1981. So this is one of them, but it's not at all easy to say what the value is. In this case, it's a half. I won't. How to get this is a pretty subtle matter. Think it over. I don't think you'll get it. How to do this, I don't have time to go into it myself. Let me just give you a brief overlook. I'm sorry, I should have left this on the blackboard, right? Let me just give you a brief overview of the theory of stochastic games. So we have existence and characterization of equilibrium. In the two-person zero-sum game, we start with the fundamental work of Lloyd Shapley, who was, I think, the high priest of mathematical game theory. There's no doubt about it. He didn't get the Nobel Prize. He should have gotten it, okay? He's the high priest of mathematical game theory. He started the ball rolling with a paper in the PNAS, the Proceedings of the National Academy, in 1953. With a discounted payoff. So today I get the full value of the payoff. Tomorrow I get alpha times that. Next day alpha squared times that. Discounted like with interest. So he solved that case completely using a functional equation. Very nice work. Bewley and Kohlberg in 1975 solved the long finite or discounted with a discount rate tending to 0. There is a limit in that case. And finally, Neumann and Mertens closed the problem in 1981 with an infinite sequence of plays. There is a value, or an epsilon value. You can get a certain amount v to within any epsilon. Now, this is where matter stood for very many years. The problem of non-zero-sum stochastic games is extremely difficult. Finally, VA in Paris, from the school of Sylvain Cerin, a student of Sylvain Cerin in Paris, Nicolas VA, not yet published, so I wrote 99 on it, but a very important, very fundamental paper, 80 pages long, proved that, so this is both difficult and important, okay? Proved that all two-person general sum stochastic games have a value. I'm sorry, not a value, an equilibrium. They don't have a value. It's an equilibrium. You can't expect a value in two-person. The n-person case has been fitfully treated by a number of people, including Elon Solan from Jerusalem, Bob Simon from Göttingen, Gosner, well, another member of Soran's team. Now, stochastic games model ongoing competitive situations where physical conditions in the future are determined by strategic choices in the present. Okay, so this is the idea over here, and examples of the environment, urban planning, transportation, also armament and disarmament, things of that nature. Let me go to the theory of repeated games, say something about that. Yeah, I think so. Yeah, we might put it back, but no. Oh, I see. Right. Yeah. No, there's nothing hidden there. So repeated games. So this is a different kind of game played over time. So it's one of a specified set of games that's being played repeatedly, but just one. Not like in a stochastic game where you jump from game to game, maybe. Just one. The players don't know which one, or some of them don't know which one. They have differential information about which one is being played. They are informed of the other's actions at each stage, and of course of their own actions, but not necessarily of the payoff. So they have to glean something about the payoff from the actions. They have to glean something about the other person's information about the payoff from what he does, okay? Now, this theory originated in a very practical application. It was a series of investigations sponsored by the United States Arms Control and Disarmament Agency, basically an arm of the State Department. This was in the 60s when there were arms control negotiations with the Russians. And the question is, what could the United States find out about the Russian arsenal by the way that they're behaving in negotiations, okay? So the consultants on this, of which your humble servant was one, first try to set this up in an abstract way, try to write specific models, and this led to a very rich and deep and extensive theory to which dozens of people contributed. Repeated games model ongoing competitive situations where information and attitudes in the future, not physical circumstances, information and attitudes in the future are determined by strategic choices in the present. We're talking about things like reputation, altruism, revenge, negotiations, and so on. I guess I should quit, right? I mean, we've gotten through about half the lecture, which is which is more than I expected, really. But as Vitaly said, we'll try to get the rest of it in the paper. So I think maybe I'll answer a question or two right now, and otherwise, I think that's it. Yes, sir. Oh, yeah, that's the important thing. Right. Certainly. Thank you very much. Let me just put that on, because that's really very important. That's very, very important. And said, let me just put this on. This won't take more than a minute or two. Thank you very much. Okay. Thank you. I'm glad you reminded me. I would have done it myself either way. Okay. Biology, evolution. So here's a game matrix, all right? We have these dots. They represent numbers. I put in two specific numbers over here. Okay, this is a game matrix of the kind that you saw before, the 2, 1, 1, 0. And the ordinary interpretation is, okay, so we have a row is a pure strategy. Ann is player 1, Bob is player 2. A row is a pure strategy of Ann. A column is a pure strategy of Bob. We have mixed strategies. For Ann is 1/6, 1/3, 1/2 as an example. Mixed strategy of Bob is 1/2, 1/2. Then we have payoffs, okay? Payoff to Ann is 3, payoff to Bob is 5. And then we have a definition of equilibrium, which I wrote on the board before already. A strategic equilibrium is a pair of strategies, or an n-tuple in general, each of which maximizes expected payoff given the other one. Okay? That is straight game theory. Transformation. Now we get to biology. Okay? It's all different. Now we have a population of bees together with a population of flowers. All right? Now we have not mixed strategies, but a population distribution. Each row is not a strategy, not something which is chosen by the players, but something which, it's a genotype. A bee has a long proboscis. He can't help it. He can't choose a short proboscis if he has a long one. And some of us also have long proboscis, and we would like short ones, but we can't choose them. Okay? So that's it. That bee. And we're not talking about one bee. We're talking about a whole population with different sizes of proboscis and so on. The flowers might be red or yellow or whatever. Okay? Now we have a fundamental concept called fitness. Now these two numbers, 3 and 5, they indicate the change in fitness if a bee with that genotype meets a flower with that genotype. All right? The change in fitness. What's fitness? Fitness is the expected number of children of an individual, the expected number of offspring. I have to say right away that this model is asexual. Okay? So we're assuming that individuals, the children of individuals are exactly the same genotype as that individual. I like to say, don't quote me on this, please, sex screws up this story, okay? It doesn't work with sex, and that's one of the open problems that I would like to suggest. What to do with sex, yes? Okay? But this is a situation. And now, so there's no choice, nobody chooses anything, nobody gets paid off, and we're not talking about a payoff and garnish, yes? That is the situation. Now, a population equilibrium, now it's not a strategic equilibrium, nobody's choosing anything. A population equilibrium is a pair of population distributions, mixed strategies, okay? Which remains constant over the generations. Nothing changes. That's what I was saying before. I'm looking at the future for population dynamics. Okay? And now, the theorem is And this is basically an insight of John Maynard Smith, although he didn't have it in such a simple form. The theorem is let me put it over here, I think it'll be more readable. A population, the concept of population equilibrium and strategic equilibrium are the same. Okay, with these interpretations, it's the same concept. A pair of strategies constitutes a strategic equilibrium if and only if the corresponding population distributions constitute a population equilibrium, if and only if. And this is under certain assumptions about how mutations work, but these are reasonable assumptions. And that maybe answers your question.
He didn't ask the question. I think that's the question.
Yeah, but I wanted to get this over anyway.
My question is as follows. I know the subject is really beautiful theory conceptually. However, a question would have any predictive value.
Absolutely. Thank you very much. Wonderful. Absolutely. There was a mind-blowing study by Richard and Hammerstein of spiders in the American Southwest. Now, these spiders in the American Southwest, it's hot, and there's not very much shade. And these spiders, they try to build Agalonopsis aperta. That's the name of the species, Agalonopsis aperta. They build these webs, and then another spider who would rather not look for a shady spot comes and tries to take over this spider's web. The idea that only human beings fight is absolutely wrong. Yes, all animals, species fight, yeah? Including spiders, the same species. So he comes to the web, and he wants to take over. Naturally, the balabayat, the owner, does not want to let him. Yes. And then the spider there who's on the web starts throwing around his weight, and the other one feels it on the web. And he says, hey, well, maybe I better clear out of here. Yes. And sometimes he goes, and sometimes he doesn't. One throws around the web. And there are a number of strategies available to the spiders. And to the intruder and to the what's the word for it? The guy who belongs there, the incumbent. The intruder and the incumbent have various strategies that they can use, and so you set up a little game matrix, and it's a non-zero sum, two-person game, where you're looking for symmetric equilibria, not just equilibrium. No, it's an intruder and invader. No, you're looking for equilibria, and how do you measure fitness? Well, you measure fitness by weighing the egg mass. I mean, these are geniuses, this Hamilton, what's his name? Hammerstein and Richard. Hammerstein is, by the way, a student of Selton. So Selton shouldn't have gotten the Nobel Prize for his work, which he certainly should have, yes. He certainly should have gotten it for the students he collected, who had a brilliant collection. So this Hammerstein, a biologist, measured the egg mass to get an idea of the fitness, and he put this into the matrix, and it was within 1% of the predicted value. So the answer is yes.
How you make this matrix beforehand?
Well, yes. Sure.
Exactly, because you make what I'm afraid, you just have an explanation, you match your matrix with the fitness. Can it done beforehand?
No, I think they did it beforehand. But yes, we know that some people, or we suspect that some scientists cheat in their work, but I don't think that they did. But I can't be sure yet. I mean, in principle, the answer to your question is yes. In practice, it's also yes. You're raising the idea that they were dishonest or sloppy or something like that. Yes.
No. This was not the question. No, the question is how, in principle, you can make this matrix before you know the fitness by knowing distribution of population.
Well, you have various strategies that you can use. Clear out at this point. Don't clear out. Clear out if the weight is over such and such and so on. I mean, you can. There is some modeling to do over here, yes, and I don't say that it's entirely chad mashma'i, but there is some modeling. But the answer is yes. I mean, they did the modeling and it worked.
It should be opposite way. Knowing that there is this equilibrium, you will measure what are correct way most important populations, like that you have equilibrium in the game.
I suggest to thank the speaker.